Proof and usage of Feynman's technique. So this technique is one of the powerful technique used in integration, used by or let's say popularized by Feynman. And what this says is, let's say if we have an integral from a to b. Okay, so let me increase its width from a to b of f of x comma y and then dx. Yeah, and if we have to differentiate this with respect to y, and if this is in the world of x and differentiate with respect to y, what we can do is we can just take it inside and make a partial derivative. That means assume x as constant and differentiate with respect to y. So we can do the partial derivative of the function and then dx. So this is said by Feynman's technique, and this is powerful in some of the integrals like this. Yeah. First of all, I will show and use, and then I will prove this formula as well. So basically, what you need to know is if you have to differentiate with respect to a variable, that's the dx is not a part of, and the function is a part of, then just differentiate with respect to that variable only, assuming x as constant, and then that is the formula. So let's say if you have integrals like this, integrals like x to the power s minus 1 by ln x, such integrals dx. In this integral, the Feynman's technique will be really helpful. So let's see how we solve this integral. So since this is in the world of x and s, let's try to differentiate this with respect to s first. And if we are differentiating with respect to x, if it goes inside, it will be a partial derivative with respect to s. Yeah, ln x and then dx. Now all the x will be a constant and s will be the variable. So constant to variable, the differentiation is constant to variable times ln of constant. Yeah, so it will be x to the power s times ln of x by ln of x. And now minus 1 by ln x, that's just constant, so that will be 0, and then dx. ln x cancels, and this is the magic of using this technique. dy by ds will be x to the power s plus 1 by s plus 1 from 0 to 1, and at 1 this is 1 by s plus 1, at 0 this is 0, so this is, and di will be 1 by s plus 1 times ds. If you integrate this, you will have I equals to ln of s plus 1 plus c. Now to find the c, then we will have the integral, right? Yeah, so we have the integral after finding c. For c, we can see that if s is 0, like when s is 0, our integral is integral from 0 to 1 of x to the power 0 is 1. So 1 minus 1 by ln x dx. Yeah, now 1 minus 1 is just 0, so this is 0 dx. And integral of 0 is just c from 0 to 1 is just c minus c, that's just 0. So I of 0 is actually 0, so that's why we can now find the value of c using this. So I of 0 will be ln of s is put as 0, yeah, so that's why 0 plus 1 plus c, and I of 0 is 0 itself. So 0 equals ln of 1 is 0 plus c, so that's why c is 0. And our integral is, now we have the answer, ln of s plus 1. This is the answer. Yeah, so the answer for this integral is ln of s plus 1. And the Feynman's technique made it really easy, because else it would have been really hard to find the answer. Now since we know how we use Feynman's technique, now let's go to proof of the Feynman's technique. Okay, so let's say we have this function g of xy as the integral from a to b of f of x comma y dx. Yeah. Now if we have to find the derivative of this function, and that is with respect to y, yeah, by first principle, that is just limit del y tends to 0 of g x comma y plus del y minus g x comma y with respect to so by del y. Now over here, since del y is just tending to 0, like there's no change in x for this limit because only del y is changing. So these two will be changing. Okay, so basically del y changing means our x will just be constant in this case. X will not vary, yeah. Okay, now after this, okay, del y tends to 0. Our g of x comma y plus del y will be integral from a to b of f of x comma y plus del y dx minus integral from a to b of f of x comma y dy by del y. Yeah, now limit del y goes to 0. Since the limits are same and okay, this is also dx, not dy. Limits are same and both of them are in dx, so we can actually subtract the integrals. So f of x comma y plus del y minus f of x comma y dx. Yeah, and we also have 1 by del y over here. Now since this integral is in the world of x, yeah, the del y will just be a constant, and constant can be taken inside the integral. Yeah, constant can be taken inside, outside, doesn't matter. So if we take that constant inside the integral, we will have f comma x comma y plus del y minus f of x comma y by del y times dx. Now also we can take limit inside the integral. Yeah, instead of here we can take this inside the integral. Yeah. Now for this, in this limit, okay, for this limit now, only y is changing, del y is changing, and x, like there's nothing to do with x. So let's just suppose x as constant, yeah. And if x is a constant, this function can also be told, like said as m of y plus del y, because constant can be removed because they don't become part of function, yeah. And this can be written as m of y just and del y. So in this case, this should have been like a derivative of m with respect to y, yeah. But here also there's x is there, and we don't want to differentiate x but just differentiate y. So that's why we have to write this as like partial derivative of y with respect to y. Yeah, we have to let x as constant and just differentiate y. So this is what a partial derivative says. Assume x as constant and differentiate y. Yeah, because only del y is changing. Yeah, so that's why there's no like difference for that's why there's no matter for x, and just differentiate y assuming x is constant. That's what this limit is saying. This thing is oversaying. So this will be integral from a to b, partial derivative with respect to y of f of x comma y and dx. So we get the result, required result, and we started with d dy of gxy. Gxy is just the integral. So d dy of integral from a to b of f of x comma y dx. So we have proved this, and I think this was our statement that needed to be proved, isn't it? Okay, so our statement is the same thing. d dy of integral from a to b f of x comma y dx is integral from a to b partial derivative of f and then dx. So we proved our statement, and yeah, we also saw an example, and yeah, that is it. And if you want to see like more of such videos introducing some advanced integration techniques, I have a playlist over here, and this is also part of that playlist. Do check this. Thanks for watching, and look forward to seeing you in the other videos.